Welcome, everybody. So I'm going to wait about a minute or two here for everybody to get in before I start start the lecture. But welcome. Hopefully, everybody found it okay and found the channel okay. So I see people coming in. So we'll wait just a minute for everybody to get in here, and then I will get started. So. All right. So today we are going to continue talking about proof techniques, section 2.1. But before I do, I want to talk a little bit to everybody about what's coming up. Because officially we have an exam scheduled for Thursday. And I feel like, given recent events, it feels a little dirty to have an exam on Thursday. I really would like to get through a certain place in the material before we have that first exam. Typically, I like to get through proof by method. Is not going to be covered today, but would be the next section. So what I'm thinking about right now is postponing the exam until Tuesday. And so I'll email this out as well, but I think we won't have an exam this Thursday. We will wait on the exam until Tuesday. Okay, so a week from today will be our first exam. All right, so what I would like to do now is let's get back into section 2.1. So we're in section 2.1 continued. And what we did last time is we did a direct proof, and we talked about what it means to prove direct implication. So what I want to do right now is let's do something. Another example. And remember, if you want to pull out your notes right now, we wrote down some axioms last time. And so what I'd like you to do is take a look at those axioms as we go through this section, because I will use them. So what I'd like to start with is let's prove that if X is less than Y, then negative Y is less than negative X. All right. So we'd like to prove that if X is less than Y, then negative Y is less than negative X. And the way that we can do this is, so proof. Notice we're proving an if-then statement. And whenever we prove an if-then statement, what we do is we assume the hypothesis and then we prove the conclusion. So my first line of my proof should be assume that X is less than Y. So if you wanted to, you could write DPI right here, that we're using the direct proof of an implication. Typically, if I just go ahead and assume the hypothesis, then we just jump into it, and we don't necessarily have to write DPI. Okay, so now what am I going to do? Well, one of my axioms, in fact, this is axiom A3, tells me that I can add something to both sides of an inequality no matter what it is. So I can add something to both sides. So what I want to add to both sides is, how about I'll add negative X to both sides of this inequality. If I do, and I said that this was by A3, then on this side of the inequality, I just get 0. And on the other side of the inequality, I get y plus minus x. And then what I'd like to do is let's add a negative y to both sides of the inequality. So I get 0 plus minus y is less than y plus minus x plus minus y. And this is also by A3. So then when I combine both sides and do a little algebra, I get minus y on this side is less than, and y plus minus y is 0. So I just get minus x on this side. And that is what I wanted to find, is that negative y is less than minus x. And so I can say, therefore, if x is less than y, then negative y is less than negative x, and we're done. Okay, so this is the proof that if we know that a number is less than another number, then if you negate both sides, that you can flip the inequality. Now, we didn't really prove that multiplying both sides of the equation by -1 flips this, although it's kind of what it looks like. But that would not be a good way to prove this, is I'd say, oh, well, just multiply both sides by -1. Well, it's like, well, we don't know what happens when you multiply both sides by -1. So be careful not to just jump in and say, I'll multiply both sides by -1. We don't know anything about that. The axioms don't tell us anything about that, so we can't use it yet. But now we do know this. Okay. So really quick, let me write some definitions. So the sufficiency proof of P if and only if Q is proving that P implies Q. The necessity proof, oops, is proving that Q implies P. Both must be proved to show that P, if and only if Q. Okay, so anytime that you get a statement and it says prove that P is true if and only if Q is true, then you actually have to write two proofs, because you have to write the sufficiency proof, P implies Q, and you have to write the necessity proof, Q implies P. Both of those need to be done at the same time in order for you to prove the if and only if statement. Okay. Somebody asked, do we need to remember the axioms for the exam, or will the axioms be provided? You will have to remember the axioms, but you don't have to remember their numbers. So what you can do is you can say this is true by an axiom, but you don't have to say it's true by axiom A4. So, but you do need to know when you make a move or a statement, like if you add a negative x to both sides of an equation, you do need to be able to say that you used an axiom to do that. So you do need to know the axioms, you just don't need to remember their numbers. Okay, so let's do another proof. I'm going to do a very, very easy if and only if proof, just to kind of show you how if and only if proofs work. And then maybe we'll do one that's more interesting. So, quick example. Let's prove that x is less than y if and only if x plus z is less than y plus z. Okay, so this is not a very interesting proof overall, but it does demonstrate what we mean when we do an if and only if proof. So when I prove something like this, I start by writing proof, and then I have to decide, what am I going to start with? Am I going to start with the sufficiency proof, or am I going to start with the necessity proof? It doesn't matter which one you do first, you just need to choose one of them. So I'm going to just start with the sufficiency proof. So in other words, I'm going to say, this is my hypothesis, this is my conclusion. And then if I do the necessity proof, this is my hypothesis, this is my conclusion, and I need to do both ones. So I draw this arrow to say, I'm going to go this way. So the first statement is my hypothesis, the second statement is my conclusion. Okay, so if I do this, that means that I'll assume that x is less than y. Okay, so we will start with x is less than y, and then I need to prove that x plus z is less than y plus z. Well, that's basically one of the axioms, is that I could add something to both sides of the equation. That's even axiom A3. So I could say, x plus z is less than y plus z by A3. And therefore, I could say that if x is less than y, then x plus z is less than y plus z. Okay, and that means I'm done with what we would call the sufficiency proof. Now I need to do the necessity proof, which now I'm going to draw an arrow facing this way to say I'm proving it starting here, going here. And so I need to assume that x plus z is less than y plus z. And I know I can still add anything I want to both sides of the equation. So I'm going to go ahead and do that. So the thing that I'll choose to add to both sides of the equation maybe is negative z. Okay, so if I add a negative z to both sides of the equation, I get that x plus z plus a negative z is less than y plus z plus a negative z by A3. I can add anything I want to both sides of that inequality. And that gives me that x is less than y, which is what I want. And so I can say, therefore, if we have that y plus z is x plus z is less than y plus z, then we have that x is less than y. Okay, so I've completed what we call the sufficiency proof. I've completed what we call the necessity proof. And so I have proved the if and only if statement. And so now I can say that x is less than y if and only if x plus z is less than y plus z. And now we're done. Okay, this is a very, very simple if and only if proof. But the point of this proof isn't so much that this is such groundbreaking news, but that this is the form of an if and only if proof. That you have to first prove one direction, then you prove the other direction, and then you can conclude the if and only if statement. Okay, so that's how we're going to go about it in general. Okay, let's do another example. Before I do, let's talk about a proof technique. And this proof technique is called proof by cases. So to prove that P or R implies Q, you must show that P implies Q and R implies Q. Okay, so if you're trying to show that an or statement implies something, and so your hypothesis is an or statement, then you have to show that each thing included in the or statement implies Q, because you don't know which one of those necessarily is the true one. So if P is the true one, Q has to be true. If R is the true one, Q has to be true. If both of them are true, then you already did it, because you said that if P is true, Q is true. If R is true, Q is true. So you need to prove both of these statements. So in some sense, if you are trying to prove an or statement implies Q, there are two proofs. There's the P implies Q and there's the R implies Q. Let me do an example of this to show you what I'm talking about. By the way, if you have any questions at any point, do use the chat. I will be looking at it. And if you have a question, just throw it up there. I may not get to it in like 2 seconds, but I'll try to answer it as I see it. Okay. Okay, so let me erase and let's look at another example problem where we use proof by cases. So let's prove that z squared is greater than or equal to 0. Okay, so no matter what real number we choose, if we square it, that number is greater than 0. Well, this doesn't look like a proof by cases problem, but it is, because what I want to do is I want to say, well, z can be different things. It could be a negative number. It could be 0. It could be a positive number. So it's kind of like I'm starting with if z is negative or z is 0 or z is positive, z squared is greater than or equal to 0. Okay, so let me start writing this down so you can see how I would do this. So proof. We know that z is negative or z is 0 or z is positive. Okay, this is one of our axioms, I believe. Let me just check on it. Oh, I guess we don't have an axiom for this one, but we do know that in the case, this is one of the axioms of the real numbers, is that if you have a number and 0, then it either has to be less than, equal to, or greater than that other number. Okay, so we know that has to be true. It has to be one of those 3 situations. So given that, I want to prove that z squared is always greater than or equal to 0. Okay, so what I could do is I could say, well, we're going to break this up into cases. So I'm going to say case 1 would be that, let's say, maybe the most easy thing would be that z is equal to 0. Okay, and so what I'm going to, my strategy here is in each of these 3 situations, I need to show that z squared is greater than or equal to 0. All right, so if z is 0, I could multiply both sides of the equation by z. And if I do, I get that z times z is equal to 0 times z, or z squared equals 0. And so I could say, therefore, z squared is greater than or equal to 0. And many times, this is when students don't like me very much. And they say, whoa, 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 whoa. No, you just said z squared is 0. So how can you say that it's greater than or equal to 0? Well, the key word there is or, right? Or says it's greater than or it's equal to 0. So z is greater than 0 or z is equal to 0. I know it's equal, z squared is equal to 0. So that means it must be greater than or equal to 0. And so this is a true statement, and that's what I wanted to prove. Okay, so that's case 1. Case 2, let's say that z is greater than 0. Okay, similarly, if z is greater than 0, then I can multiply both sides of the equation by z. That's one of my axioms, is that if you know that a number is bigger than 0, then I can multiply both sides of the equation by it. So I could say that z times z is greater than z times 0. Or we would say, and what is the axiom we're using right there? We're using axiom A4. Or another way of saying that is that z squared is greater than 0. But if z squared is greater than 0, then z squared is greater than or equal to 0. Therefore, z squared is greater than or equal to 0. Similar reasoning, if it's greater than 0, then I can OR on anything I want to. And so what I want to OR on is that z squared is equal to 0. So it's greater than or equal to 0. So now let's write down our third case here. So case 3. Or maybe I should use my Roman numerals since I started with Roman numerals. So case 3 would be that z is less than 0. All right. So if z is less than 0, this is a more interesting one because I can't just say, let's multiply both sides of this inequality by z. And the reason I can't do that is because I can only multiply both sides of an inequality by z if z is bigger than 0, not less than. So it'd be really nice if I knew something that was greater than 0 that I might be able to multiply both sides of this inequality by. But remember an example I did right at the beginning of class. I said that if z is less than 0, then if I negate both sides, I can say, so that means that 0, well, is, how do I want to say this? I should say 0 is less than negative z. And remember, that was by an earlier example that I just did. So if I negate both sides of this, the sign flips. And so I get that 0 is less than negative z. So negative z is a positive number. But if negative z is a positive number, then I can multiply both sides of an inequality by negative z. How about I multiply both sides of this by negative z? If I do, I get that z times negative z is less than 0 times negative z. Or I get that negative z squared is less than 0. Now I want to use that same example. By the way, I just used one of my axioms right here. Which one did I use? I multiplied both sides by a positive. That's A4. So I want to use that same example again and negate both sides. But if I negate both sides, I get, therefore, 0 must be less than z squared by my earlier example problem. And that's what I want. Not quite. No, therefore yet. I got that 0 is less than z squared. That's not what I want. I want to say, therefore, 0 is less than or equal to z squared, just by logic. Okay. Now, so what I did is I said, z is less than 0 or equal to 0 or greater than 0. If z is 0, z squared is greater than or equal to 0. If z is positive, z squared is greater than or equal to 0. If z is negative, z squared is greater than or equal to 0. So no matter what I do, z squared is greater than or equal to 0. And so therefore I can say, therefore, z squared is greater than or equal to 0 in all cases. And we're done with the proof. So this is actually something that comes up a lot, is that it's very hard to prove something for all cases of z at the same time. So what we have to do is, instead of just doing one proof to prove that z squared is, say, greater than or equal to 0, we have to say, okay, there are actually some cases here, because z could be negative, z could be positive, z could be 0. And in each of those cases, I need to prove the result. Okay, so in this case, there were 3. You could have a problem where there's 10 cases. You could have a problem where there's 100 cases. I don't think you're going to experience anything like that in your homework or anything, but you definitely could come up against something where it's more than 2. That's not uncommon at all. Okay. Any questions that I can answer for anybody who's online right now? This would be a good time to ask a question. And I'll get the board erased. Okay, so here's a question. How come you needed to multiply the z less than 0 by -1 for case 3 before using axiom 4? Yeah, good question. So the temptation would be, why don't I just multiply both sides by z? And the answer is because z is negative. And I don't know how right now. Obviously, if I was in algebra class, I know how to multiply both sides of an equation by a negative number. But honestly, right now, we don't know what to do. We don't know how to multiply by both sides of an inequality by a negative. All we know right now is how to multiply both sides of an inequality by a positive number. That's in the axioms. Multiplying by negative numbers, not in the axioms. So I can't multiply both sides by z. But since I know that negative z is a positive number, then I can multiply both sides of the inequality by the positive number. So you've got to use the axioms. Okay, so that's something you have to be aware of and be careful of, is that you don't use knowledge from algebra that you're like, oh, I know this. It's like, well, you only know things if they're in the axioms. Okay. Another quick question. How can we use examples as a reason? Is it only when we proved it earlier? Yeah. So if you prove something in class, like in your homework, or you prove it in an example, or I've proved it in an example, then you can use it as reasoning. And you can just say something like I did, like a previous example problem, or a previous homework problem, or a theorem that we had in class, or an example problem we had in class. You don't have to write example we had in class. You can just say example. So if you're using a result that we've already proved, just cite it, and then you're good to go. But you do have to cite it. Okay, so that's the one thing that you have to be a little bit careful of, is don't just say things and don't give any justification. It's just like, that's obvious. It's like, that doesn't work. You have to say, I know what I'm talking about. This is coming from something we did previously. Okay. Let me write down something about absolute value. So here's something that's kind of confusing sometimes to even up to calculus students, is what really is absolute value? Well, if I were to define the absolute value of A, I would say, whoa, drop the pen, that the absolute value of A is equal to A if A is greater than or equal to 0, and it's equal to negative A if A is less than 0. Okay, and sometimes when people look at this definition for the first time, they don't like it very much because I say that the absolute value of A could be negative A. But when you really think about it for a second, it makes perfect sense. So if I say, what's the absolute value of 3? Then we would say, well, the absolute value of 3 is 3. And I would say, yep, that's right. But what are you really doing? You're saying, okay, the absolute value, if it's positive, just leave it alone. So you can take the absolute value signs off if it's positive or 0. So we do. What if I said, what's the absolute value of negative 3? The absolute value of negative 3 is, everybody knows, 3. And you say, well, look, that's not negative. And I said, well, I never said that negative A was a negative number. Because really what 3 is it's minus 3. So what I'm doing is I'm taking the number inside, and if it's negative, I negate it. And negating the negative number makes it positive. So what you do to a negative number when you take the absolute value is you multiply it by -1. Right, to make it a positive number. So it does make sense that the absolute value of A sometimes can be negative A if A is a negative number. Okay, but this is an important definition, and we're about to use it to prove some things. One other way of thinking about absolute value, and actually this is the right way to think about absolute value, is the distance that a point lies from the origin. So if you just said, if you thought of absolute value of A as saying, how far is A away from the origin, you would be right. Okay, so, and as you get into higher level math classes, that's even more the way you should be thinking, is what I mean by the absolute value of A is what's the distance A lies from the origin. Okay, but for now, this is a perfectly good definition, and we're about to use it. Okay. So, an example. Let's prove that A is less than or equal to the absolute value of A for all A in the reals, the real numbers. Okay, so we want to prove that for any value A, that A is always less than or equal to its own absolute value. All right. So how do we do this? Well, I think that the best way to go about this is similar to what we did in the last example, is there are some cases here that A could be greater than or equal to 0. And in that case, we do something. or A could be less than 0. And in that case, we might need to do something else. So that's how I'm going to start this proof, is I'll say proof that we know that A is greater than or equal to 0, or that A is less than 0. And in both cases, I need to show that A is less than or equal to its own absolute value. So let's start with case 1 and say that A is greater than or equal to 0. Okay, then let's consider the absolute value of A. Well, what is the absolute value of A if A is greater than or equal to 0? Well, the absolute value of A is A. Correct? So A equals the absolute value of A. But if A equals the absolute value of A, then A is less than or equal to the absolute value of A, just by ORing on the less than. Okay, so this is just by logic. And that's what we wanted to show, is that A is less than or equal to the absolute value of A. So now we have a second case. So case 2 is that A is less than 0. So now let's consider the absolute value of A. Well, the absolute value of A, what do we know about the absolute value of A, if anything? Well, we know that that is equal to negative A. Right? And so the question is negative A less than or equal to this guy? Well, let's see. What I could do is I know something about negative A because I know that A is less than 0. So since A is less than 0, I could say that we know that 0 is less than negative A. Correct? And that's by our previous example. Again, I said that if A is less than 0, then 0 must be less than negative A by our previous example. And so now I know that A is less than something and 0 is less than negative A. So that means that A is strictly less than negative A. And what is our justification? I believe it's A1, but let me look. Yep, A1. So I have A is less than 0, 0 is less than negative A. So A is less than negative A. But negative A is the absolute value of A. So that means that A is less than the absolute value of A, and therefore A is less than or equal to the absolute value of A. So if A is greater than or equal to 0, A is less than or equal to the absolute value of A. And if our second case, if A is less than 0, then A is less than or equal to the absolute value of A. In both cases, I can say, therefore, A is less than or equal to the absolute value of A for all real numbers. And we're done. Okay, we have a question. Let's see. Is the real number something that we know the definition of? Yeah, so our knowledge is based on axioms. Yes, so right now what we can say is like these axioms, A1, A2, those axioms, they're the axioms of the real numbers. So they're kind of like, we have these things we call the real numbers, which are like, you know, the integers, the fractions, the irrational numbers like pi and the square root of 2. We have all these numbers, and A1 through A5 are some rules that we know about the real numbers, or that we are assuming to be true about the real numbers. So that's a really good question. Do we know about the real numbers? It's kind of like, well, yes, we can consider the real numbers as a class of objects, and then we're going to put some rules on the real numbers, which are the axioms of the real numbers. So for right now, yes, we can assume that we know what the real numbers are. But that is a good question. Like, maybe, do we know anything? It's a good question. Okay. Other questions before I move on? So this gives us a pretty strong foundation, and what I mean by proof by cases is sometimes you need to break something up into cases, but then for each case, you need to prove the result. Okay, so you might end up doing multiple proofs to do the larger proof. Okay. So that is all that I have for section 2.1. So 2.1 homework is officially assigned. Because of the weirdness of what's been going on lately, I am going to make section 2.1 homework due on Thursday. Usually I make things due on Tuesday, but I want to keep moving and I don't want people hung up on that. So 2.1 homework will be due on Thursday in class. Okay, let's start section 2.2. So section 2.2 is more proof techniques. Okay, so the first proof technique in this section is proof by contradiction, or so also called an indirect proof. Okay, so proof by contradiction is also known as an indirect proof. So this is kind of how it works. We've kind of talked about this before when we were doing logic-based proofs. So let me write really quick. What does this mean again? So we assume the hypothesis and the negation of the conclusion and show that this leads to a contradiction. Okay, so when you do a proof by contradiction, or also called an indirect proof, what you want to do is you assume the hypothesis, and you get to assume the negation of the conclusion, whatever that is. And then after doing both, assuming the hypothesis and assuming the negation of the conclusion, you try to show that that leads to some sort of an absurd statement. Okay, and as soon as you find that absurd statement, you have proved that P implies Q by the same logic we worked through earlier in the class. Okay, so that's what we call a proof by contradiction. We'll try one or 2. Let me see. So are the homework problems posted on Foxtail? Yes, they should be posted on Foxtail, so you can just get them there. Let's do an example. Okay. Again, we're kind of starting small here. Some of these contradiction proofs aren't super, super crazy, but they are good examples. So example, we have prove that if x is less than or equal to y and y is less than or equal to x, then that means that x equals y. Okay, so we want to show that if x is less than y and y is less than or equal to x, then x equals y. Now, right off the top of this is something that we just know is true, right? And sometimes it can be a little bit tricky to prove things that you already know are true. That can be very challenging at times, that to prove something you already know. So what we're going to do is, even if I started with a direct proof and I said, so x is less than or equal to y and y is less than or equal to x, it's kind of like, okay, so where do you go from here? It may not be clear, but if we do a proof by contradiction, this becomes sort of easy. So proof. So remember, if I'm going to do a proof by contradiction, I get to assume the hypothesis, and then I get to assume the negation of the conclusion. So I'll assume the hypothesis. So assume that x is less than or equal to y, and that y is less than or equal to x. Now I get to assume the negation of the conclusion. The conclusion in this situation is x equals y. So I'm going to suppose, and remember this is my fancy symbol to say, I'm about to say something that I don't actually believe, but I'm going to say it's true. So I'm going to suppose that x is not equal to y. Okay. So I know that x is not equal to y, correct? So if x is not equal to y, then I get the following. So I have two cases. Well, I know that both of these are true, correct? But if x is not equal to y, then x has to have one of two relationships with y. Either it's less than y or it's greater than y. Okay, so let's just break it into those two cases. So that means that x is less than y or x is greater than y. So case one, let's just say that x is less than y. Okay, but if x is less than y, that's the exact negation of y being less than or equal to x. So if this one is true, then y being less than or equal to x is not true. So this is actually a contradiction. So I'll say this is a contradiction because y is less than or equal to x. It contradicts that y is less than or equal to x. And case two would be that y is less than x. But this is also a contradiction because I know that x is less than or equal to y. So either way, this leads to a contradiction. And so what I suppose to be true must actually not be true. So I can say, therefore, that means that x must equal y. Okay, so then I can conclude that if x is less than or equal to y, and y is less than or equal to x, then x must equal y. And I'm done. Sound good? Okay. Let's see. Let's do another one. So on this next one, I'm going to have to give you a little bit of a heads up on something because it comes up in the proof and I don't want anybody going, what is he talking about? And that is that if x is positive, then the square root of x is also positive, is something that I'm going to use in this proof. And I want everybody to just kind of buy the story right now. Is that obvious? Somewhat obvious. It's not one of our axioms, but it's almost like by definition. It's kind of like if you have a positive number and you take its square root, by definition, that square root is a positive number. And you might say, well, wait a second, what about the negative of, aren't there two square roots, a positive square root and a negative square root? And I would say, yes, there are. But the thing is, typically when I say something like x squared is equal to 4, then I say that x is equal to plus or minus the square root of 4. The square root of 4 is what? Without the plus or minus, the square root of 4 is 2. We never say that the square root of 4 in and of itself is plus or minus 2. The square root of 4 is a positive number, and then we put the plus or the minus in front of it. So if we talk about a number, the square root of x, where x is positive, that by definition is positive, okay? That's the definition of a square root, is the positive number that when squared gives you x. So the square root of x has to be positive by definition. And I'm going to use that in this next proof. And I just didn't want anybody saying, now hold up, couldn't the square root be the negative one? And it's like, no, it cannot. It has to be the positive one. Okay. That said, let's write down a problem here. So example, prove that if x is greater than 0 and x is less than y, then we have that the square root of x is less than the square root of y. Okay, so I think that you'll find that this would actually be sort of challenging to prove, okay? That if you try to do a direct proof of this, this would be difficult. So the way that we're going to go about this again is we're going to try to do this indirectly, or a proof by contradiction. I have some. Let me see if I need to respond to him. Okay. So, yeah. Yes. Nothing I need to answer. I just have to laugh. Okay. So let's go ahead and prove this. So again, if I'm doing a proof by contradiction, the way that you go about that is you assume the hypothesis and then you suppose or assume the negation of the conclusion. So the hypothesis in this case is I assume that x is greater than 0 and that x is less than y. So those get to be true. Then I suppose the negation of the conclusion. So I'm going to suppose that the square root of y is less than or equal to the square root of x. Okay, and then I'm going to show that that's no good. That can't be true. But if the square root of y is less than or equal to the square root of x, then there are actually two different things that it could be. Either the square root of y is less than the square root of x, or the square root of y is equal to the square root of x, one or the other, right? So let's write that down. Let's see. So we have that the square root of y is less than the square root of x, or we have that the square root of y equals the square root of x. So I'm going to break it into two cases. So case one will be that the square root of y actually equals the square root of x. Okay, if that's true, then let's look at x. X actually is the square root of x squared by definition. Okay, and what I'd like to say is, well, the square root of x is the square root of y. So that means that this is the square root of y squared, just by substitution. But the square root of y squared is what we call y. So I used substitution here. I just substituted in the square root of y for the square root of x. And then you see we get that x equals y. But what do I know? I know that x is less than y. It's not equal to y. So that's a contradiction. So this leads to a contradiction because I know that x is strictly less than y. It's not equal to y. Okay, so that's case one. Let's look at case two. And the other case would be that square root of y is less than the square root of x. Okay, so this is where I need to use a little knowledge about the square root. So we know that the square root of x is a positive number, right? Because x is a positive number. So if x is positive, then the square root of x is positive. Can I say that the square root of y is a positive number? I'd like to. I think I can because I know that 0 is less than x is less than y. So since 0 is less than x and x is less than y, that implies that 0 is less than y by, I believe that's a 1. So I know that 0 is less than y, so that means that the square root of y is also bigger than 0. So I have that 0 is less than the square root of y. So I know that this square root of x is bigger than 0 and the square root of y is bigger than 0. Okay, so now I want to use that knowledge. So if something is bigger than 0, I can multiply both sides of an inequality by it. Okay, and the inequality that I'd like to multiply it by is that the square root of x is greater than the square root of y. So let's multiply both sides of that by the square root of x. Okay, if I do, I get that the square root of x times the square root of y is equal to the square root of x. Oh, not equal to, I'm sorry. This is less than. Is less than the square root of x times the square root of x. So I just multiplied this inequality on both sides by the square root of x. Now let's also multiply that on both sides by the square root of y. By the way, this says that the square root of x times the square root of y is less than x. Now let's multiply both sides of this inequality by the square root of y, which we also know is a positive. So I get that the square root of y times the square root of y is less than the square root of x times the square root of y. Or y is less than the square root of x times the square root of y. So look what I have here. I have y is less than the square root of x times the square root of y, and I have that the square root of x times the square root of y is less than x. Combine those using A1, and I get, therefore, y is less than this guy is less than x, so y is less than x by A1. But I know by assumption that x is less than y. So that must be a contradiction. This is a contradiction because I know that x is less than y. Okay, so in case one, there were two cases, this one or this one. Case one led to a contradiction. Case two led to a contradiction. So what I supposed right here, that must be false. So I can write, therefore, since that thing must be false, I have that the square root of x must be less than the square root of y. And therefore, if x is greater than 0, and x is less than y, then the square root of x must be less than the square root of y. And we're done. Okay, I have a couple comments here, so I'll try to answer them. Because we showed a contradiction in case one, could we just stop there? No. So you can't just stop there because basically it could be that one of them leads to a contradiction, but the other one is true. And if the other one is true, then it actually could be the case that the negation happens. What you're trying to show is there's no way that the negation of the conclusion could ever happen. It doesn't matter what which of these two things is true. The negation of the conclusion cannot happen. So you have to show that in each case, the negation of the conclusion leads to a contradiction. So no, you can't just do one of them. It's a good question. It would be nice if it were true. Somebody answered, can you go over the jump to the first or line to the following line again for case two? Okay, good question. Let's see. I'm trying to find exactly what you mean. So can you go over the jump to the first or line to the following line again? Let's see. So from here to here, is this what you're asking? Hopefully just put in yes if that's the case. So from this or line to this line, is that correct? Okay, perfect. So what I'm saying is, so I used one of the axioms. Actually, I should have written it down right here, that I can multiply both sides of the equation by a positive number. I can't remember if that's A3, but I'm just going to put axiom. And so to get from here to here, I just simplified this. To go to here, what I did is I took this inequality again, and I multiplied this inequality on both sides by the square root of y. And I knew I could multiply it on both sides by the square root of y because the square root of y is positive. So this is like, this line doesn't follow from this line. This line is independent where I say, look at this, multiply both sides of this thing by the square root of y, and that gives me that line. Does that make sense? Hopefully so. Okay. So the last proof technique that I want to talk to you about today is called a proof by contrapositive. So let's write something down about it. So proof technique is proof by contrapositive. Okay, so in a proof by contrapositive, you assume the negation of the conclusion and prove the negation of the hypothesis. Okay, so this is kind of like a brother to the proof by contradiction, but it is different. So what you do is you don't assume anything about the hypothesis. You only assume the negation of the conclusion. Then you actually prove the negation of the hypothesis. So in other words, you're proving that P implies Q is logically equivalent to not Q implies not P. That's what you're doing. Okay. Oops. Okay. Let's try one of these. So an example, let's let M and N be non-negative integers. Prove that if M times N is less than 100, then M is less than 10, or N is less than 10. Okay. Now, what I think is challenging here is that if you were to try to prove this directly, you would get to assume that M times N is less than 100. And that's it. Okay. And then you have to prove that one of the two is less than 10, which intuitively seems sort of obvious to us, that one of those would have to be less than 10 for that to happen. But to prove it directly is very challenging, actually. So, and you can think about that for a little bit. Like, how would you prove that directly? And it's very hard. So, but a proof by contrapositive makes this actually very simple. Let me show you. So, proof, I get to assume the negation of the conclusion. So the conclusion is M is less than 10 or N is less than 10. So we have to be very careful here because we're negating an or statement. And when you negate an or statement using De Morgan's laws, the or becomes an and. So it's going to be not this thing and not this thing. Okay, so be very careful here because if you leave it as an or and forget to change to an and, it's all out of whack. But let's try this. So I get to assume the negation of this guy, M is greater than or equal to 10. And I get to assume that N is greater than or equal to 10. Okay, so now what I'd like to do is let's look at M times N. So let's consider the value M times N. Well, M times N, we know that M is bigger than or equal to 10. We also know that N is bigger than or equal to 10. So what I could do is I could say, well, M times N then is greater than or equal to what? 10 times 10. And 10 times 10, of course, is 100. Or so, M times N is greater than or equal to 100. But I said at the beginning that M, in the original problem, M times N is less than 100 is the hypothesis. What's the negation of the hypothesis? It would be that M times N is greater than or equal to 100, which is what I just showed. So I just said that if not Q, then not P, which is logically equivalent to P implies Q. So now I can just conclude, therefore, if M times N is less than 100, then M is less than 10, or N is less than 10. And we're done. So what seems to be a very, very difficult proof, if you're proving it directly, becomes almost a trivial proof if you're doing it by contrapositive. Okay, a couple questions. Let's see. Why do you use assume instead of suppose when you're assuming the negation? Good question. Because so why am I using an assume statement here and not a suppose statement? The reason is because I'm never going to go back and say that's not true. So when I use a suppose statement and I use this little, I've got it erased, but when I use my little suppose, what I'm doing is I'm making a mark to myself that eventually I need to go back and say that the negation of that thing is actually true. In this case, I'm actually doing like a direct proof. I'm doing a direct proof, but I'm just using not P and Q for the direct proof. I'm using not Q and not P for the direct proof. So a proof by contrapositive is a direct proof. You're just starting and ending at different places. Instead of starting at P and ending at Q, you're starting at not Q and ending at not P. So if you think of it that way, a contrapositive proof is actually a direct proof, not a contradiction proof. Okay, a contradiction proof is almost like a whole different thing. Hopefully that answers your question. Another question, it's a bit confusing to me what sort of things we can use in a proof, like -1 times -1 is 1. Yeah, what sort of things can we use in a proof other than axioms? Okay, so what can you use? I think you can use like equality algebra. So like if you're trying to say that like x equals y and y equals z, so x equals z, that's fine. What you don't know as much about is inequality algebra. So what the axioms kind of are all about is how do you use inequalities? Not equality. So I think that everything that is like equals based, and you're saying like if you were saying -1 times -1 is 1, is equal to 1. I'm like, sure, we know about equality. What we're proving things about right now is inequality. So if you want to use equality statements, I think we're good with all of that. If you're going to use an inequality statement, be very, very careful what you're talking about, because that's what we're kind of playing right now that we don't know anything about. Okay. So hopefully that's helpful as you do your homework, is if you're making like here, I said that 10 times 10 equals 100. And I didn't say, well, is there an axiom for that? No, we know like basic arithmetic around equality, but we have to be very careful if we're going to say something about greater than or less than. Okay. Let's see. Yeah. Other than that, if in doubt, justify. So if you're not sure whether or not you need a justification, ask yourself, do I have a justification? And sometimes it's just like basic algebra of equality. If you're in the case of an inequality, you really should be asking the question, do I really know that? And if the answer is no, you should think about it more and come up with the justification. So at this stage in like your mathematical career, you should be always asking yourself, do I know what I'm talking about? And that's going to treat you well. I think we're about out of time. So thank you, everybody. If you have more questions about this stuff, feel free to come by and chat with me. We're not having a test on Thursday. That's the big news, right? Don't worry about a test on Thursday. On Thursday, I really want to go over the next section, which is on proof by mathematical induction. And if what everybody tells me is true, Lemons will be open on Thursday, and we will be able to get back into the building. So plan on having class, regular time, regular place on Thursday. No exam. We'll talk about the exam on Thursday, and hopefully that will be good. Okay. Well, thanks, everybody. Have a great day, and I will see you then.